Okay. Good evening. It is Monday, the 31st of August, 2020. This is Calculus. This is lecture 2A, formal definition of the limit, and two cops and a drunk. My name is Scott. The nameplate now appears behind me. Don't know about that. Interesting. Are there any questions before we begin related to the material from last week? From last Thursday. I would remind you that you may speak in Twitch chat, but if you do so, it is public. Twitch chat is over there. You may speak in Twitch chat, but it is public. Also, you may speak in Discord chat, and that is private. And I have added to my little studio space, I now have a computer which is running the two text streams separately so that I don't accidentally share everybody's name again on Twitch. So I've got the Discord server. I've got Discord on a separate computer so that when I accidentally hit screen one again, it doesn't broadcast people's names. So that seems to be fixed. Do we have a test soon? Yes, we have a test on, if you look at the schedule, 3 weeks from last Saturday. So we've got Monday, Tuesday, Wednesday, Monday, Wednesday, Friday, Monday, Wednesday, Friday, Monday, Wednesday, Friday test. 9 classes remain, counting this one. So that's when the first test is. Again, you can check the syllabus, and you can check the for the exact date. But I've got it on the calendar as well. Are there any questions? Other questions, comments, issues, suggestions, or thoughts? Okay. So let's go ahead, and it's on limits, everything. It's on basically module 1. So if you pull up the syllabus, cancel. Do I have the syllabus readily available? I do not. So if you pull up the syllabus, the test, the next test is the first test is on September 19th. And it is on this stuff. So everything regarding limits and the definition of the derivative. And if you scoot down to the bottom, you can actually see the sections it covers. So it covers everything up to this day here. Proving the power rule. So basically all of chapter 1 and then 2.1 and 2.2. Okay. So let's see. So last time we talked about the definition of a sequence. And we talked about the and we ended with the definition of the limit of a function as the function went to infinity. As x went to infinity. Oops. So today we're going to pick up the definition of the limit in the first big theorem. Now, the next week, we're going to, so today we're kind of stealing a lecture. So what I'm going to do is I'm going to do the formal definition of the limit today. And we're going to talk about some visualizations to kind of get a handle on these definitions and things like that. The plan is on, as you can see here, Wednesday, we're going to talk about how to write proofs for this class. So I know that people say proofs, and all of a sudden everyone has, these nightmare flashbacks, PTSD type things from high school geometry. It's not like that. They're not like table proofs or anything like that. What we want are good mathematical arguments. So we're going to talk about that on Wednesday and what to write, how to write it, and we'll have this first big theorem, two cops and a drunk, to play with on Thursday when we do it. Then on Monday, we're going to be doing continuity in the intermediate value theorem next week. So next week, we're going to do continuity in the immediate value theorem. These should all be Monday, Thursday, shouldn't they? Then we're going to be using infinitesimals to deal with limits. That's the new material that I sort of did last semester, but I'm going to do it much deeper because it really helps with a bunch of those problems from test 1. And then the following Monday, we're going to do the definition of the derivative. Derivative is a function. And then Wednesday, of course, we're going to prove the power rule. And then that Saturday is test 1. And of course, it shouldn't be Wednesday. These should all be things like Thursday. That's nice. There we go. So that's what it should look like. So, and I mentioned this last time. Remember, this was the stuff that's developed last. So what we're doing today, where we're going overall, is that we want this idea of a formal definition of the derivative and an intuitive notion about what that means. So for fixed x, and I'll get into this more when we do the definition of the derivative, but we need this concept of a limit. How does this slope, what values does a slope get closer and closer and closer to, this difference function here? What value does it get closer and closer and closer to as h goes to 0? Does it get closer and closer to a particular value? And if so, what? Okay, so that's kind of this idea here that we're going to be picking up about this. Now, we're also going to have this idea of a ratio of infinitesimals. So we've got two ways to think of the derivative, formally and informally. And the names here, I mentioned this last time, these names are getting, 1805 to 1859. And then look at this one, 1918 to 1974 for Robinson. So this is not ancient math. This is the newer stuff. And then we're in a sense going historically backwards. We're starting with this newer stuff first, and then going back to what Newton, Leibniz, and then finally what Archimedes had in mind. Which is, again, a little different, but it's the way they wanted to do it. So it's how we're doing it. Okay. So, and everybody's talking in chat about dinner very meanly because, of course, I haven't eaten yet. So, of course, I can afford not to eat a little bit. So, there's that. So that's kind of where we're going. One thing I do want to kind of polish off. I didn't mention this last time, and I should have, or not last time, the time before last. There's this function called the identity function. And I don't want to spend a lot of time on it, but I do want to mention it. It's this idea that I have this function where f of x just equals x. I'm sorry, the thing's poking out over here. That's annoying. My cat was messing with things, and now she knocked the right, the green screen is not covering that because my cat knocked things aside. And I think that's as good as it's going to get. So ignored that little artifact there in the corner. So yeah. So I wanted to mention this. This is this identity function where I've got this set x. I don't care what x is, but I've got a function that goes from it to itself. So here, the y space are the same set. Okay, and this is called the identity function. And all it does is take x and map it right back to itself. So it's, f of x equals x, which is 1 maps to 1, 2 maps to 2, 0.5 maps to this. It's 0.5 maps to 0.5, 2.5 would map to 2.5, pi maps to pi. It's the thing that does nothing. And its graph looks like this, right? It's just the straight line. This is called the identity function. And people were a little confused about this before. I don't know why this thing got knocked down. It did. That annoys. But it's just this straight line function, or the function that maps everything just back to itself. I need to mention it because we're going to use it today. Okay. So as I said today, we're going to do this formal definition, and then we're going to do some visualizations, and we're going to finish with a function with no limits, the Dirichlet function, and then we're going to state two cops, and that'll be it. Are there any questions so far? Okay. All right, well, if you recall last time, we had this definition of a sequence, and we had this idea, right, that if I'm heading toward some number, L, the sequence kind of heads toward that number. So, for example, I had this idea like Sn equals 1 over n, then S2 equals 1/2, S3 equals 1/3, and so on and so on and so forth. And I had this idea that the limit as n went to infinity of 1 over x equaled 0, right? Because no matter how far away, how small of an epsilon I made, I could get close enough to get to 0. I could get closer than that epsilon and stay closer to that epsilon. So I had this idea of the margarita I could never escape. And if you looked at this as like as a arrow diagram, it would look something like this. Right? Here's, the natural numbers up here. And if I do this, here's 0. And if I do this, 1 maps to 1, 2 maps to 1/2, 3 maps to 3, to 1/3, 4 maps to 1/4, 5 maps to 1/5, 6 maps here, and you get this idea of it getting closer and closer and closer to 0. Okay, so how do we feel about that 1 to 5? Okay. All right. So the key to this thing was this idea of an epsilon, of arbitrary closeness. Okay. Right? I have this idea that no matter what it is, I'm going to land inside this little bit. So here, I've got 0 minus epsilon, 0 plus epsilon. And this right here is really n. Right? So, because every day thereafter, I'm landing inside the thing. All right. Now, we concluded with the same idea, except instead of natural numbers, instead of a sequence, I'm now stopping and putting myself, I'm now okay with it being a function. This, who cares, right? It's got some leftward stopping point. It could be negative infinity, but the point is it includes some interval, including infinity. And L is some number in the Y space. And I'm going to start being very right. L is a. So I want to kind of keep this kind of straight. Alpha is an X space thing, and L is a Y space thing. I want to keep track of which is which. Okay? And so I have this idea that f of x goes to L as x goes to infinity if for any arbitrary distance away, any arbitrary epsilon, there exists this alpha so that if x is greater than alpha, f of x is in this little zone here. So this is the formal definition of a function as x goes to infinity. How do we kind of feel about that? It is not so much that I want you to know the words. You don't need to memorize the words. You need to see the words. But it's really this concept here, this graph as a concept. Okay? I'm more interested in kind of the graph concept. The fact that at some point, everything after that lands within epsilon, no matter what I make epsilon. So to go to 1 over x again, then if epsilon equals 0.01, right, then for all alpha, right? So that's the idea. There's, for any epsilon you give me, right? If you gave me 0.001, I give you 1,000. You give me 0.801, I give you 1 with 8 zeros back. And that will get within an epsilon of 0. Because the limit equals 0 in this case. How do we feel about that, 1 to 5? Okay. All right. So, well, let's look at this definition one more time. What this thing really says, right? What this thing really says, if we just like copy and paste this little bit down here. Now, let's just copy this bit here and just paste it here. Let's look at this. Okay, that didn't work. It copied the text, but it didn't copy any of the formatting. That's nice. Let's look at this. F of x to 0 if, let's just look at the end of it here. So we've got limit as x goes to infinity of f of x equals L if. Now, let's see. The for all epsilon, that stays. Now, there exists alpha in D in the domain so that let's get rid of this. For any x greater than alpha, f of x, which is our y value, is in L minus epsilon, is in this interval L minus epsilon, L plus epsilon, which was this picture here, right? anything greater than alpha, I land, my y value winds up in there. For any x here, y is here. And what I want is to build the same notion, but of a limit from the left at a finite point. Well, infinity's not really thing. Yes, epsilon is any number. You give me the epsilon, I give you back the alpha. Okay? So, for instance, if you gave me the epsilon 0.01, I could give you back the alpha 100. Okay? And in fact, no matter what epsilon you give me for this example, right? No matter what epsilon you give me, I can give you 1 over epsilon back, and I'm fine. Right? For any positive epsilon. So it's not any number, it's any positive number. And it's not an easy definition. So don't worry about not getting the definition perfect. Think about the concept. Again, of the definitions, this one's developed last. Well, there's nothing in particular special about this idea x greater than alpha. Let's rewrite this. Right? This is an interval. If x is greater than alpha, that means x is within the interval alpha infinity. Okay? So, if I wanted to adjust this to have a limit at a finite number, I'm just going to move the x space away from infinity. I'm going to have us approach from the left of a number. We'll call it a. So here's the idea. Instead of having alpha, I can have something like this. Let me see. How do I do this? So I can get something that looks a little like this. Okay. Where's the black pen? We want this to be A and alpha. So if I want something other, if I want this to be 0 instead of infinity, I'm just going to kind of move right here. My statement was way over here to the right, right? As I went to infinity. What I'm going to do is I'm just going to move everything back. So instead of infinity, I'm going to have some value A. So I'm going to write the following. I'm going to write basically the same thing, except I'm going to replace everywhere I see an infinity, I'm going to replace it with A. So the limit as x goes to A from the left of f of x equals L if, same thing before, for any epsilon greater than 0, there exists alpha. I'm not going to say where alpha is yet, but I'll just say less than a, so that for any x in, now instead of saying for any x in alpha infinity, I'm going to say any x in alpha a. F of x is in L minus epsilon, L plus epsilon. So here, a equals 0 and L equals 0. Now, I had an epsilon here. Notice here that if my y value is here, okay? If my y value is in here, there is some point after which I cut off this function from the left and I land closer to 0 than this epsilon distance. And the picture is what's important. I want you to get the idea that the picture is what's important, okay? So I'm moving from a situation where I'm here and this picture, and I'm moving toward a situation where I've just moved this interval back. So as I get closer and closer and closer to L, I get closer and closer to A in this space. Or as I get closer and closer and closer to A, as I get closer and closer to 0, my values move closer and closer to 0 in the y space. Because in the y space, it's L. So how do we feel about that, 1 to 5? Okay. Yeah, I see crying emojis. I see 5s. Wow. Okay. And again, the picture is more important than the words for this class. My TA is in analysis now. The words are important in that class. But for our purposes, we need the picture, not the words. Okay. Well, let's just clean up the words a little bit. I want something to be symmetrical, right? I said for every epsilon greater than 0, there exists an alpha less than a. Wouldn't it be nice if it was something else? So I'm going to let alpha equal a minus delta and change everything to that. So now instead of alpha less than a, there exists alpha less than a. I'm going to say there exists, there exists delta greater than 0, so that for any x in a minus delta, comma a, f of x is there. So now it's a little bit more symmetric. Okay. And again, don't feel stupid. This is the hardest single concept, the hardest definition that we go over the entire class. And it happened on the 3rd day of class. Because of this thing, right? This is much more modern than the concept of a derivative and the concept of an integral. This definition is really, really, really hard. Okay? And you don't need the precise definition for calculus. You need to see it. but you don't need to have it memorized or be able to apply it quickly. What you need is this concept. You need the idea behind the definition. You need the idea about an arbitrary space in Y corresponding to a space in X. That if I made this small, I could make this small enough to make it fit. So that everything on the left landed in here. Everything on the left up to delta. Okay? So I don't want you to get hung up on the definition. I want you to get this concept. Arbitrary closeness is what's important. Okay? And again, arbitrary closeness. That's what I want. Okay. All right. There's an example in your notes. Example. Show that the limit as x goes to 0 of x squared equals 0. Right? Okay. So what am I going to do? Well, I'm going to let and some of these are actually easy to do. So you gave me an epsilon, and I said, okay, let's take the square root of epsilon. Okay? Now, if x is in 0 minus delta, 0 plus delta, x is between the square root of epsilon, 0 minus the square root of epsilon, 0 plus square root of epsilon. Therefore, y is in epsilon, negative epsilon, comma, it's actually in 0. Right, if I square something negative, I actually wind up on the positive side. I'm sorry, I want to do limit from the left. That's my bad. Now, if x is in this, right here, that means that x is in negative square root of epsilon 0. And therefore, y is in 0, comma, epsilon, which is the square root of epsilon squared. Okay. Which is a subset, if I want to say it, of 0 minus epsilon, 0 plus epsilon. In other words, if x is less than square root of epsilon to the left of 0, y is less than epsilon away from 0. And that looks like this. Or I can just use the version that's in the notes. And that looks like this. And hence the drawing, right? If I'm in this blue area here, I'm going to wind up in that red area there. Okay, how do we feel about that one, 1 to 5? That's really, really hard. Okay, so don't feel bad if you don't completely get it. And there will be a little bonus WebAssign on this. A few questions. I'll set it up. But it's not, again, the idea is the graph. It's the picture that is really important for this class. It's not the definition. It's the picture. It's the associated picture that's more important than the definition. The definition is horrible, but this idea of arbitrarily close is what's important. Okay? So don't feel like overwhelmed by this. All right? This is really, really hard, and the picture is what's important. Okay. Are there any questions? Okay, so I've managed to make it so that people don't have questions because they're unhappy about the thing. Okay. I'll tell you what, let's look at it instead of looking at it like this, let's look at it from let's look at it from here. Let's look at it like this. Let's look at it from a graphing point of view. Okay. So here's the graph that I'm talking about. This corresponds to that arrow diagram I had before. Now, okay, this is just off Desmos. Let's take a little snip and look at this. So that corresponds to that picture there. Okay. Now, let's look at this. In my y space, I have this idea of epsilon. In this case, it was 0.5. Here's epsilon. And epsilon is a y number. Now, it's actually L plus epsilon, where L is 0. And here is L minus epsilon, where again L is 0. Now, I have this X space concept. And is there a point, if I back this off, right? There's some point here where everything after that lands in here. And that's the idea. There's some point here where everything after that lands in there. So everything from this X corresponds to Y's in here. And that's this idea of heading toward, but it's formalized. Okay. How do we feel about that? This kind of formalization of this whole process. Okay. Okay. So some people like the graph, some people like the arrow diagram. I'm an arrow diagram person myself, but graphs, make more sense to a lot of people. And so I'm heading toward, and that's this idea. Okay. Well, what can mess up? Obviously, I can have a jump, right? If I have a jump, I've got no limit, right, from either direction. So let's look at a couple things that can mess up. Something like this. Right? This has no limit as x. So here's a mess up. Right? So this function, by the way, has a open circle here and the closed circle here, right? So here, if I put a sufficiently small epsilon away, right? I should say this does have a limit from the left and it does have a limit from the right. But if a equals 0 and I say L equals 0, which is not, right? The limit here equals 1 as I go from the left, right? But if I suppose that it's 0, okay? So that's a mess up. Here's another one. This right here, mess up. The limit as x goes to 0 from the left of sine of 1 over x. This thing oscillates back and back and back and forth. In fact, it's the same thing we had before with sine of x as we went to infinity. It's the exact same thing, right? It doesn't settle. So if we look at sine of x as we went to infinity, we'd have the exact same problem. So let's do, let's see. In orange, what does it say? After the 0.5 note. Oh, you mean this? If epsilon equals 0.5, then there is no delta. That works. The same thing could happen here. This is the exact same thing. Right? These two have the exact same problem. 1 over x is x goes to 0, and sine of x is x goes to infinity. Right? They've just, I've just kind of flipped it a little bit. But it's the exact same problem. Right? It doesn't settle as this one doesn't settle as I get close to 0. This one doesn't settle as I get close to 0. This one doesn't settle as I get close to infinity. Okay? They're just flips of the same coin. Okay. All right. So, how do we feel about that? 1 to 5. Okay. Well, if I wanted to find the limit from the right, what would I do? Well, let's see. Let f from D to R, where D is some interval. Let A near D. So what I mean by near is I'm allowing it to be endpoints. Okay. Don't get hung up on D. Let L be a real number. And actually, it's not one of the, it's the in D or the left endpoint. Okay. So, and again, don't worry about that. That's really not important. The limit as x goes to a from the right of f of x equals L if for all, you know what? I don't even want to write it again. What do I need to change in this definition? That's it. And I'm done. That's the whole change in definition that needs to happen. Okay. How do we feel about that? That's the only thing I need to change. Oops. That's not working. And there's the picture that corresponds to it. Okay. All right. So, same thing. All right, let's do something cool. Okay. Let's do a function that has limits nowhere. All right, this is called the Dirichlet function, after our guy at the top here. Dirichlet, sorry. Okay, so I'm going to let f of x equal 1 if x is rational. And 0 otherwise. All right, so recall x is rational if there is a whole number an integer p and positive integer q so that x equals p over q. Okay? Now, if x equals p over q, right? Here's the thing about rational numbers. They're dense. And here's what I mean by that. If I have any two rational numbers, can I always find a rational number between them? So for any two rational numbers, is there always a rational number between them? So if I give you the numbers 0 and 1/2, what is a rational number between 0 and 1/2? 1/4. Right? Now, if I give you 0 and 1/4, what's a rational number between 0 and 1/4? 1/8. If I give you 0 and 1 over 100, what is a rational number between 0 and 1 over 100? Well, 1 over 1,000 will do it, or 1 over 200. Right? There's always, so between any two rational numbers, is another rational number. Now, between any two numbers that are not rational, okay, or between any two rational numbers, is an irrational number. Okay? How do you feel about that, 1 to 5? Between any two rational numbers is a number that's irrational. All right. Oh, I'm sorry. These two things. Between any two rational numbers is an irrational number, and between any two rational numbers is an irrational number. Okay? Okay. Now, that's going to give us a very strange function. Think about what this does. Between any 2 points, any two rational numbers is another 1. But between any two irrational numbers, between any two rational numbers is also an output of 0. So this thing is going to look like this. It's a weird function. Right? So no matter where I put my epsilon, if I put my epsilon if epsilon is 0.5, there's no delta up here. Every delta okay? No matter where I put my delta, I'm going to wind up with a number that goes to 0 and a number that goes to 1. It's dense. So this has no limits. Okay? How do we feel about that, 1 to 5? No matter where I put my delta, I'm going to wind up exiting the function. And it's a weird one. It's kind of cool. Okay. Okay. Delta could be either rational or irrational. It doesn't matter. The point is that in any interval, I don't care what delta is, if delta is greater than 0, then f of x equals 0 for some x in a minus delta a, and f of x equals 1 for some x in a minus delta a. Because the point is that a minus delta a, I don't care what a is, I don't care what delta is, as long as delta is greater than 0, is going to have a number, is going to contain a rational number, and it's going to contain an irrational number. And because of that, one of those will map to 0 and one of those will map to 1. There is a much easier definition right there. The two-sided limit. The limit as x goes to a of f of x equals L if both of these things are true. The limit from the left goes to L and the limit from the right goes to L. Now, isn't that a much simpler definition? Woo! How do we feel 1 to 5 about this definition right here? Okay. Okay. So let's look at a function that's a little bit harder to work with. So let's consider the following function. Let's look at sine of x over yeah. Let's look at sine of x over x. That one's not as nice. Let's look at something else. I'll have to delete that. Let's do... Ooh, no, we can't do that. That looks really ugly. Oh, I know why it's not working. I'm sorry. I've got the scaling all bad. So let's look at this function here. Let's look at sine. This function here. This function here is f of x. Oops. This is f of x equals x times sine of 1 over x. Now, remember that sine 1 over x, yes, you are allowed to be here. Remember that sine of 1 over x had this problem. It didn't settle near 0. But if I do x times sine of 1 over x, it sort of does. And the question is, how can I show? We can see this intuitively, right? That here I've got a limit. Both sides are kind of going to 0. All right. And I want to show that the limit as x goes to 0 we'll do from the right, of f of x equals 0. I want to show this. And what I'm going to use is this thing called 2 cops and a drunk. Okay? And here's how 2 cops and a drunk work. I have a drunk with one of those little beer hats on. Okay, my drunk person looks like a penguin. And I have 2 cops. Okay? Now, here's what's going to happen here. Let me group drunk up. Now, drunk is going to move like this. Okay? Up and down, swaying around as he goes in time this way. And here's the paddy wagon. And so what's going to happen is that the cops are going to wind up getting the drunk in the paddy wagon, right? Because the drunk is going to go this way and want to go this way and this way and this way. But my 2 cops are going to be nice, straight, and arrow, and are going to keep between the drunk. So it's going to wind up looking a bit like this. I should have had this open already. I didn't. My bad. Okay, there it is. No, it's not going to run. So this is what's going to happen, right? I've got two cops. Oops, I accidentally got rid of cop. And the cops are going to stay between the drunks. The cops are going to escort the drunk to the paddy wagon. Hence the thing, two cops and a drunk. And usually when I do this, I do it in class with a little demonstration, and it's funny. And I was trying to make it work here and be funny, but it's not. So that's what's going to happen. Okay? How do we feel about this idea? Here's the statement of the theorem. This is kind of the picture to keep in mind. The statement works like this. So the point is of this theorem is that I'm trapped between the two. Okay? All right. So, and there's the statement. Well, how does this work? Well, here, let's do from the left instead of from the right. There it goes. And of course, there's left-handed, right-handed, and two-handed versions of this. But look at this function. This really bad function is trapped between that function and that function. So this function right here, top of x equals negative x, and bottom of x equals x. So it's the case that for all x less than 0, sine of 1 over x is, sorry, it's sine of 1 over x. Is that what I said? I'm sorry. Right? For all x less than 0, negative 1 is less than or equal to sine of 1 over x is less than or equal to 1. So multiplying through by x, I get, and remember x is less than 0. Negative x is greater than or equal to, because remember I flip, x sine 1 over x is greater than or equal to x. So let top of x equal negative x, bot of x equal x. Notice the limit as x goes to 0 from the left of top of x equals the limit as x goes to 0 from the left of negative x, which equals 0, and the limit as x goes to 0 from the left of bot of x equals the limit as x goes to 0 from the left of x equals 0. Therefore, by 2 cops, the limit as x goes to 0 from the left of x sine 1 over x equals 0. Okay. How do we feel about that, 1 to 5? I know I'm 3 minutes over. So here's the statement of 2 cops and a drunk. And I will be going over this again and again and again. Because it's one of our key theorems. Let me see if it's already on. Let me see if the graphic's up. Nope. Yep, there it is. So if you want the picture of it, here's the picture. Let's see, how do I get there? So this is on the screen. I think I need to fix this because it's missing. This is class 2B and this should be 2A. But here's the picture, okay? So as I move in, right, F is trapped between top and bot as you get to here, after this point here. And then, because they're all headed toward the same place, right? Because they're all headed toward L in the Y space, right? Because it's trapped between them, that means F must be heading to L. So here are 2 well-behaved functions, top and bot, and F is stuck in between them. And because F is stuck in between them, after some point left near A, I go to the same spot. And yes, the other name for it is the old, boring, dull squeeze theorem. Also known as squeeze theorem. Boring, boring, boring squeeze theorem. I like 2 cups and a drunk better. It's more descriptive. Okay, so today what we went over was we went over the formal definition of the limit. Now, this is very important. What I want is for you to get the picture. You don't need the definition, but you do need the picture. You need kind of the idea about what's going on, and that's from the picture. Okay? And then what I want, and then we went over kind of these visualizations. Again, the picture. And we went over the formal definition of the two-sided limit. It's easy. The limit from the left equals the limit from the right. And then we did a function with no limits, the Dirichlet function. And then we stated 2 cops and a drunk. Expect that to be on a quiz coming at you on Wednesday, and probably a couple more. People that know me know that when it comes to the big definitions and theorems, I tend to put them on a lot of things. And we also stated where we were going, and that's going to mean that this definition is now fair game. Maybe on Wednesday, definitely by Monday. Are there any questions? Comments, issues, thoughts? F. Is that the grade that I get on this lecture? Is that what's going on? Okay. All right. So if there are no more questions, I'm sorry I went a little bit over. And I will talk to everybody on... Oh, and this is the last one of the really, really big theory. Next time on Thursday, what we're going to get is into the idea of how to write these things up. And then on... and again, so that's where we're going. Thursday, we're going to get into writing it and using this sucker and what all it means. Because 2 cops and a drunk is going to be one of our big theorems. All right. Anything else? Okay. Well, good evening.